This is about the module 3B to design a seawater desalination. The last lectures we discussed about how to design and different seawater desalination plant and what we have to study and what are the processes and what kind of pre-treatment required, reverse osmosis and post-treatment. And this class will mainly focus on key terms used to describe membrane processes. So there are several terms which are required to design seawater desalination. So in terms of flux and then module element, and we can also learn how to utilize the same terminology. And water quality parameters are very important, and this is how we can get this water quality impact for designing this desalination plant, and introduce the reverse osmosis, what's the main mechanisms and how this membrane looks like. So we will cover this kind of lectures. So what are the key terms to describe the membrane processes? So flux. So this is what the flux is about. Throughout per membrane permeate area. So we just utilize water flux. So membrane pass through this water molecule, and then we just utilize as liters per hour per square meter. So we just say LMH. So when you have liters, how many water pass through the membrane, and 1 square meter, and then hours. So we call the LMH to design your membrane process. So in the US, they utilize gallon per square feet per day. Also, we have to make sure balance of the driving force and resistance to flow. So permeate is about the water treated by membrane. So we have feed water, concentrate, and permeate. So this permeate, often called filtrate in microporous applications, and permeate common term is in SWRO, NF, and sometimes ultrafiltration. And concentrate is about the concentrate waste from membrane, sometimes called reject or brine on reverse osmosis and nanofiltration. So in your assignment, so you can see what's the high concentration of brine or reject concentrate impact when you discharge the after desalinated water. So this concentration will go back to ocean. So how this will impact the overall ecosystem of seawater. So recovery is permeate over feed. So this is important when you design your seawater desalination. So let's say 50% of recovery. This means you have 1 liter per hour feed water, and then you will collect 0.5 liter per hour permeate, and then 0.5 liter per hour concentrate will go back to ocean. So that this recovery, depending on your design, is very important. And transmembrane pressure. So this is important because driving pressure across the membrane. So how much pressure you have to apply. So when you have very severe fouling, so this transmembrane pressure will change significantly. So we have to stop your process, and then you have to also calculate the TMP to produce your permeate And transmission is passage of a certain solute across a membrane. So opposite of the rejection, transmission is equal to 1 minus rejection. So when you have a rejection transmission, so 99% of the salt rejection in seawater, and still 1% pass through the your membrane. So we have to calculate the permeate our concentration to make sure that the drinking water quality. So rejection transmissions are very important to design our seawater desalination plant. Unit is grouping of a membrane and passes with common feed pump, piping, and controls. Element is individual membrane unit, and module is individual membrane unit, but this terminology is utilized for porous membrane, microfiltration, ultrafiltration. Element is basically from reverse osmosis, nanofiltration. Also cassette, already you have experience to design membrane bioreactor. So individual membrane unit for your submerged membrane cassette, ultrafiltration, microfiltration, CIP. So in a certain stage you need to go through your cleaning because membrane will foul, and this we call clean in place. So chemical cleaning or physical cleaning can be utilized for CIP. Backwash is intermittent reverse flow to remove solid, and enhanced backwash is reverse flow with brief chemical dosing used to increase the CIP interval. So chemical enhanced backwash is enhanced flux maintenance. So next one is water quality parameters. Essential water quality parameters are very important to design a seawater desalination plant because we can make a better selection of pretreatment and reverse osmosis membrane. Also, we can predict organic fouling, inorganic fouling, and biofouling. So let's look at what's the source seawater quality parameters. So turbidity levels above 0.1 mg per liter are indicative of high potential for fouling, and spikes above 50 NTU for more than 1 hour would require sedimentation, pretreatment, or dissolved air flotation treatment prior to filtration. So high NTU will damage the pretreatment, so that we have to utilize the DAF or flocculation sedimentation process before filtration process. And total organic compounds. So if you think about the summertime and wintertime, so microbial activity is more active during summertime, and we have a more organic compound. So if below 0.5 mg per liter, biofouling is unlikely. So above 2 mg per liter, biofouling is very likely. So during the summertime, more organic concentration, so biofouling effect will be much higher than wintertime. So depending on the area, so we have to consider this total organic carbon concentration. In general, in Sydney, we have almost less than 1 mg per liter of total organic carbon concentration, which is relatively safe for biofouling impact. So salt density index, SDI 15. So this source seawater levels consistently below 2 year-round typically indicate that no additional filtration pretreatment is needed. and SDI more than 4, so pretreatment is necessary. So what's the exactly meaning of SDI? This is the concept of SDI. So SDI is calculated number based on filtration of a sample through a 0.45 micro filter pad. So SDI readings are used to indicate the fouling tendency of water for use as RO feed water. So let's look at this setup. And we have nitrogen gas, which required for the pressurizing the your water, and this is the seawater to measure SDI, and this is the membrane, which is the 0.45 micrometer filter fat, and this one you can pass through your seawater and then measure your water flux. So you can measure SDI following formula. SDI 15 is equal to 101 minus T1 over T2, and 15. So T1 is the time in second to filter initial 500 millimeter of sample. So seawater initially 500 millimeter collected, and then how many seconds we measure. And T2 is time in second to filter final 500 millimeter of sample. So after 50 minutes, it's allowed to pass through between timed sample interval. So first 500 millimeter, and after 50 minutes, and we measure again T2 in seconds to filter final 500 millimeter of sample, and utilize this equation. So when you have more than 4 of the SDI, so you have a very bad water quality. So you need a pretreatment to reduce the SDI and protect the reverse osmosis. So this SDI is important when you have a RO membrane warranty. So if you have a high SDI, very bad water quality, which will lead to causing your RO membrane and pretreatment. So when you have a contract with a membrane company, so they try to make a warranty when you have a less SDI more than 5, so they don't have any warranty period. However, your water quality is less than 5 or 4 SDI, so they can have a good warranty timing when you have your feed water quality. And total suspensed solid is needed to access the amount of residuals generated during pretreatment, so does not correlate well with the turbidity and beyond 5 NTU. And iron concentration is one of the essential parameters, because if iron is in reduced form, the seawater RO membrane can tolerate up to 2 mg per liter. If iron is in oxidized form, like iron oxide, Fe2O3, and concentration more than 0.05 mg per liter would cause accelerating fouling. So you have very oxidized iron oxide can easily combine together with the other compound, and this will create the membrane fouling. Manganese is very much similar. If manganese is reduced form, SWRO membrane can tolerate up to 0.1 mg per liter. If manganese is oxidized form, concentration more than 0.02 mg per liter would cause accelerate the fouling. So when you remove this kind of manganese iron, so we need extra treatment such as flocculation process. Same as silica. concentration higher than 20 milligram per liter may cause accelerated fouling. So we need to analyze for colloidal silica concentration. If concentration is more than 20 milligram per liter, so we have to consider what kind of pretreatment process is required for silica removal. And chlorine concentration higher than 0.01 milligram per liter would cause RO membrane damage. As I mentioned last class, chlorine is the oxidization, so can damage the RO membrane polymer. Temperature less than 12 degrees would cause a significant increase in water energy use. Temperature more than 35 degrees may cause accelerated mineral scaling and biofouling. Temperature more than 45 may cause irreversible RO membrane damage. Also, oil and grease, pH. Already we discussed about the pH last meeting. Additional parameter also we need to consider carbon dioxide, bicarbonate, and carbonate. So this is the buffering capacity, which will combine with the calcium carbonate or phosphate and the magnesium carbonate, which will generate inorganic scaling. Acidity and alkalinity, hardness such as magnesium and calcium. Phosphorus, total dissolved solid, which is related to osmotic pressure. So seawater has 35 grams per liter, 3.5%. Osmotic pressure is almost 30 bar. So we have to consider how much hydraulic pressure has to be applied, and then recovery can be obtained. And barium sulfate, strontium sulfate, and disinfectants are very important for designing your seawater desalination plant. So basically, essential water parameters is water chemistry. So what's the solubility of different compounds in seawater, and what's the saturation point in terms of their inorganic scaling potential and the organic biofouling potential. So I'm sure that most of students do not have chemistry background in water, so very difficult to calculate. That's the reason why we need the computer-aided software to predict our water quality parameters. So as you can be seen, this is the one example from our software, so WAVE. So you will study about details later on for this class, and this is the water quality parameter. So first you collect your water, and then just put all the different known concentrations such as ammonia, potassium, sodium, barium, or some CO2, bicarbonate, carbonate, and then sulfate was different temperature, pH, and turbidity, total suspended solid, SDI, and what's the concentration of organic compound. So you can see all the feedwater sample, what's the type of seawater, surface water, well water, wastewater, so what kind of pretreatment you are utilizing. So this will provide all the your water chemistry when you recover your seawater more than 50%, and what kind of inorganic scaling and organic scaling, biofouling scaling can be predicted from this software. That's what it is. You don't need a very strong water chemistry background, because this software will tell you briefly what kind of potential for your membrane fouling. So we will study more detail how to design this wave software. SWRO, let's look at the history. So when we started from this SWRO, first seawater desalination in Kuwait, 1956, and desalination commercial plant construction, 1970. And we have had the leading desalination market at the time by distillation. The problem was energy consumption was very high, 10 kilowatt hour per cubic meter. So just boiling, and then your energy consumption is almost more than double of reverse osmosis. And first energy reduction, desalination to reverse osmosis happened early 1990 to 2000. So reverse osmosis membrane innovation and then growth. So this is the first technology innovation period. And since 2005, so a lot of commercial opportunity and produced the leading desalination market by reverse osmosis, and energy cost almost 4 kilowatt hour per cubic meter. So this is the second technology innovation. So look at the distillation 10, and nowadays we can operate energy reduction by up to 4 kilowatt hour per cubic meter. So we can study for reverse osmosis how to design better rather than this. So what's the RO membrane? So this is the general size and different contaminants. How can we remove? So let's look at the 1 micrometer. So human hairs around 10 to 100 micrometer, beach sand 1 millimeter to 100 micrometer, activate carbon. So let's look at the less than 1 micrometers. So this is the range of nanofiltration and reverse osmosis. So nowadays the coronavirus is one of the big issue. So virus size is the 0.005 micrometer to 0.1 micrometer. So coronavirus is around 100 nanometer size, 0.1 micrometer. So when you remove this virus, so we need to utilize the ultrafiltration or nanofiltration. So this is the nanofiltration range. Nanofiltration can remove sugar and then some of the endotoxin compound, dyes. And when you try to remove the sodium chloride, which is the most abundant concentration in seawater, and salt, and the metal ions and atomic radius. So sodium's size is almost 0.6 nanometer, and chloride is a little bit bigger size. And then if we separate from pure water H2O less than 0.6 nanometer size, and then we have to utilize the reverse osmosis membrane. So we have to design this kind of membrane to separate your sodium chloride from seawater, and only pure water can be extracted from your. So RO membrane nanofiltration, very much similar mechanism. So non-porous membrane, so membrane thickness increased, permeate flux decreased. So active layer as thin as possible to produce the more higher flux. And membrane structure is asymmetric. So some nanofiltration was membrane have a same asymmetric. So symmetric is the different, like a microfiltration, ultrafiltration. However, RO membrane nanofiltration consists of asymmetric membrane. So we just call thin film composite membrane for nanofiltration and all reverse osmosis. So let's look at the RO membrane element and membrane structure. So you can see this is the RO element. So you have a lot of layers. We just call spiral wound the membrane element, and this is the microscopic membrane. So you can see there are 3 layers for RO membrane. First layer is ultra thin skin layer. Second layer is polysulfone support layer, and last layer is the backing layer. So you can see that this skin layer we just call polyamide thin film composite. So we just call the TFC thin film composite RO membrane. So this skin layer polyamide can separate your salt and pure water. So the pore size is almost 0.6 nanometer, and water molecule will pass through, and then you can separate your salt and pure water. So this skin layer is very important. However, this skin layer is 20 nanometer of thickness, so very weak, so that we need to have support layer for the polysulfone polymer. So just polysulfone, and then we pressurize the 60 bar. So this pressure has to be tolerated from this membrane. That's the reason why we have third layer of the backing layer. So if we look at the more detail, so this is the 20 nanometer of skin layer, active layer, and this is the polysulfone support layer, and this is the non-open backing layer. So 3 layers consist of RO membrane. Let's watch a video of thin film composite RO membrane. So this video is animation to better understand how this polyamide TFC RO membrane produced and polymerized, and how we utilize this membrane to separate salt and pure water.
To create our standard spiral wound membranes, we construct the flat sheet membrane using Hydronautics automated casting equipment. We begin the process with a fabric support base and then coat it with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water. The semi-permeable polyamide layer consists of a thin film of polymeric material a few thousand angstroms thick, formed on a porous supporting material, flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane surface. The leaves of membrane and feed channel spacer are then combined with a sheet of permeate spacer on 40-inch long membrane element. The permeate water then flows out the end of the vessel and is collected as the product. and the reject or concentrate from that vessel may then flow through another vessel producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed. Typically 70 to 90% of the water can be recovered as pure product water.
So this video shows how you produce the polyamide RO membrane, how you can create the element and put into the pressure vessel. Then finally you can utilize the as a seawater desalination application. So understand, and this is the transport phenomenon of reverse osmosis membrane, and mass transport across membrane is the diffusion, and osmosis is very important, so we need to understand better of osmosis and concentration, polarization, permeate flux, which is limited by osmotic pressure and concentration polarization, apart from the intrinsic, the membrane resistance. And so what's the osmotic pressure? So you have a feed water, very low concentration of salt, and brine, very high concentration of salt. In between we have RO membrane. So when you have this condition, so what happens is that water, pure water, low salt concentration will pass through your membrane, and then you have a water head. So your high concentration, high osmotic pressure will suck your water molecule through your RO membrane, and then you can create your natural osmotic pressure. So we just call forward osmosis. And opposite meaning is reverse osmosis. So we pressurized here and then push it through your water molecule to the lower concentration, and we just call reverse osmosis. So when you look at the nature, so what kind of osmotic pressure can be applied? So this is cherry. So cherry has very high sugar inside your fruits, and then sugar has a high concentration and high osmotic pressure. So when you have water, rainwater, and water will stay on the surface of cherry, and this water molecule, then skin layer of the cherry is almost a membrane. So water molecule will pass through because of the sugar osmotic pressure, and then you can burst out this cherry if you have a very high concentration of your sugar, because water molecule will pass through and then make them bigger and bigger. Finally this cherry will be burst out. So let's look at the compounds: sodium chloride, magnesium sulfate, and SWRO seawater. So when you have a sodium chloride 1000 milligram per liter, and osmotic pressure is 1 kilopascal, which is 1 bar, and so magnesium sulfate 1000, which is 25 kilopascal, 0.25 bar, and sucrose is sugar, which is similar to cherry sugar concentration, has very low osmotic pressure because this is the organic salt, so it's not fully ionized in water, so that the osmotic pressure is relatively low. And the seawater 35 gram per liter has around 227 bar osmotic pressure. So how to calculate the osmotic pressure? So Bandt equation can be applied. So in 1901, so this Bandt received the first Nobel Prize in chemistry for this work with solution. Osmotic pressure is equal to concentration and ideal gas constant and temperature of your solution. So when you have a high concentration, you have a very high osmotic pressure, and ideal constant is fixed, and temperature is the solution. So when you have a high temperature, you have a high osmotic pressure because you can dissolve your salt, and solubility is higher. And we have to be consider what's the dissociated solid. So let's have one example for how to calculate your osmotic pressure. Calculate the osmotic pressures of the following aqua solution. So 3% of sodium chloride. So molecular weight is 58.45 gram per mole. By weight, 3% albumin. It's an organic compound. And then 65 gram per mole by weight. And the suspension containing 30 gram per liter of a solid, where the particle weight is 1 nanometer, is equal to 10 to the power of minus 9 at a temperature 25 degree. So we have this Bandt equation, and what's the osmotic pressure. So can you stop your video, and then you can calculate this osmotic pressure to better design your osmotic pressure. How about your answers? So I hope everybody got correct answers. So we utilized the Bandt equation, and this is the 30 gram per liter of sodium chloride. So molecular weight of sodium chloride is 58.45 gram per mole. So we have a 30 gram per liter of concentration. So just change the unit, and this 8.31 is the constant value. This is the Kelvin temperature 298. So if you calculate this one, so you will get your data. However, you have to be a little bit careful for dissociated solute. So we have two here. So when you put your sodium chloride in water, so sodium changed to ionized form, and sodium cation and chloride anion. So we have two species will affect this osmotic pressure. So we just put 2, and then this will give this value, and then this Newton per square meter unit change will give your answer 25.4 bar osmotic pressure. So let's say it's a magnesium chloride, MgCl2. So Mg cation has 1 ion, and then Cl2, MgCl2, Cl2, 2 ion. So we have 3 dissociated ion. So this dissociated solute have to be changed to 3. So depending on your solute ionized form, so we can consider what's the osmotic pressure. Albumin has no dissociated solute, so we have only 1. So this is the 65 gram per mole, and then 30 gram per liter concentration, IL, and then temperature. So we have this 0.01 bar pressure. And suspension, just a particle. So we just utilize this 6.02 times 10 to the power of 23 number, and then 30 concentration and R value, K value, and finally we have a very low osmotic pressure for suspended material. So this is the way we can calculate osmotic pressure, but you know that seawater contain very different concentration of salt ionized form, so we cannot really calculate very detailed osmotic pressure. In this case, we have two options. One is total dissolved solid. So you can simply measure conductivity, which can convert total dissolved solid, and we can roughly calculate what's the concentration of your salt, and then convert to your osmotic pressure. And the other way is you just put all the detailed salt concentration, and then utilize the software like a wave, and then it automatically calculate your osmotic pressure in terms of concentration and different species. So that's the way we can calculate the osmotic pressure for your seawater desalination plant design. And this is the osmotic pressure way of your recovery way. So we have feed water, 36 gram per liter of salt concentration, and this is the RO membrane, and flow rate 50% of the recovery. The flow rate of feed water and flow rate brine is goes to this way, and then water molecule pass through, and we have almost less than 250 milligram per liter of permeate concentration. So this is the osmotic pressure 30 bar here, and then your osmotic pressure is almost 60 bar in brine, because this is the 50% of the recovery. So energy consumption 3 times the theoretical limit, 3.5 kilowatt hour per cubic meter. So reverse osmosis recovery can be calculated based on permeate flow over feed flow. And concentration polarization. So this is the very unique terminology for reverse osmosis membrane. So what's the meaning of this CP? Solute concentration at the membrane surface is higher than bulk concentration a distance away from the membrane surface. So diffusion from the membrane surface back to the bulk solution. So back diffusion can be enhanced by a cross-flow high shear rate. So let's say this is seawater, and salt concentration, you can see the sum of your dot, and this is the membrane. So pure water will pass through this membrane, and you have accumulated salt and then higher concentration of your salt. So with your membrane length, so your concentration polarization layer of your salt concentration is higher. So this is the bulk concentration, 35 gram per liter, and then you have a membrane surface concentration. So depending on your concentration polarization layer, so your real osmotic pressure, real concentration of your osmotic pressure is different from bulk osmotic pressure. So we need to also consider this concentration polarization to better design your osmotic pressure between your membrane feed side and permeate side. So real osmotic pressure difference will occur between this membrane, and then concentration polarization will be a real osmotic pressure your design of seawater desalination. So all RO process are in cross flow mode to limit this CP effect. So you have a very high cross flow, and then you will wash out and make a turbulent and reduce your high concentration of your salt on the membrane surface. And water movement across membrane and net driving pressure. So we can calculate your permeate flow is equal to water permeation coefficient, membrane area, and net driving pressure. So this pressure, how much you apply, and you will get the different permeate water flow. So this coefficient, depending on your membrane, so manufacturing company will provide this membrane coefficient and membrane area. So how many membrane you apply, and then you will have a more permeate water flow. So here, so net driving pressure can be calculated with pressure feed water minus your osmotic pressure minus half of your pressure difference minus permeate flow pressure. So based on this net pressure, so we can easily calculate how much water can be produced and flow can be obtained to design your. So let's have one example. So RO unit is to demineralize 750,000 liters per day treated effluent, and pertinent data are permeability coefficient 0.2 liter per square meter day kilopascal at 25 degree. Pressure difference between the feed and product water is 2500 kilopascal, 25 bar. And osmotic pressure difference between the feed and product water is 300 kilopascal. So lowest operating pressure is around 10. Temperature is 10 degree, and determine the membrane area required. Membrane area correction is 1.58 at 10 degree. JW can be calculated A and delta P minus delta pi. Here delta P is pressure on feed side pressure, and delta pi is osmotic pressure of feed, osmotic pressure of permeate, and AM is membrane permeability coefficient, or we just say hydraulic permeability. So you can stop this video and calculate this example. So the answer is 2,690 square meter. So based on this flux calculation, so water flux, so 0.2 water permeability coefficient multiplied by your pressure difference 2500 kilopascal minus 300 kilopascal of your osmotic pressure. So you will produce then your water flux 440 liter per square meter of membrane per day at 25 degrees. So in the question, the membrane area is what's the membrane area at 10 degrees. So A is equal to, we need to calculate total amount of water flux, 750,000 liters per day, and we also calculate 400 overall water flux from this membrane, and this is the temperature factors. So when you have a high temperature, you have a higher water flux, and lower temperature, lower water flux. So we need to calculate 1.58 the temperature factor. So you will get 2690 square meter. So based on this water flux, we can calculate how much water capacity you have to design, and then we can select your membrane element, and then we can calculate how many membrane area required, and then we can easily purchase the membrane and install to produce your total amount of water flux. So thank you for your attention. I will see you next lecture video.